Hello, everyone. This should be the culmination and the final video about the DIY LiDAR scanner from our very own ENME 435 course. The project, of course, is one that uh, has had a couple updates through their videos. And for one last time, it is LiDAR time. So, in terms of the team, the people involved in this is Mohammed Abu Musa, yours truly, the professor, the man, the myth, the engineer, Dr. Stephen Mitchell, uh, the very own cursed tripod that has given me many strange glances while I'm skating through campus, holding it like a wand or a lance of some sort. And then I don't know who this lady is, Oyusufuro. So, in terms of the project timeline, this went through a couple steps. First, we learned what LiDAR was. Professor Mitchell was very helpful in breaking down decently complicated tech in terms of the specifics of it into simple, easily digestible pieces. After that, we had to mess with tolerances to do with 3D prints and making our very own rig, because each person in the course had to sort of figure it out on their own, an engineering challenge, if you will. Of course, after a week, after I got it more or less working, 3D print broke. So we try again and learn from the mistake. The info went up a lot. After that, Dr. Mitchell sort of led us through coding time. And then near the end of it, good old homework 8, we actually messed with a mesh, which is a hell of a statement. All right, so in terms of our target, let's recap. The target in question is the Brendan Iribe Center for Computer Science and Engineering building. Now, CompSci sort of take ownership of the building, but that doesn't mean we can enjoy it too. The reason I chose it is because it has a couple sort of central pillars to make this thing work. It had major shapes that I could try and replicate using the LiDAR. So it had straight edges, so we can see how successfully we wrote those. It has soft curves, we can see that. It has different elevations. And then a final sort of challenge for the scan would be, can we get a certain level of resolution so that we can see the etch to engraving? Those words are engraved directly. We'll find later that we cannot, and the only way to do so is to take an order of magnitude more scans. But yes, we'll see how we got to it. So, in terms of the setup, I'll let this guy do all the talking. Actually, I'm doing all the talking. So, our setup is pretty basic. It had two main electrical components, which is the Arduino at the bottom and the Raspberry Pi at the top. The Raspberry Pi was connected to a camera, which is our main sensing module. The Raspberry Pi powered our line laser. A battery pack behind it powered both components. A mount held it towards a tripod that was then later sort of elevated and upgraded to a mouse, like a mic stand, which would come in use later to find different angles. Now, beyond finding a rig, we had to actually map this thing. Now, I visited this thing more times than I can count with multiple sort of iterations to try and fix things. On the left was the latest one. On the right was the first. And we faced multiple issues. So, first of all, always charge your laptop. Second of all, noise is the bane of any sort of sensing, and one must deal with the noise. As you can see on the right side, I rudimentally tried to fix the noise issue by being a human shield. Now, I realized this was not practical and not very consistent. So you'll find that in the left video, we sort of see it again. Me trying to tackle it, but this one was a lot more consistent. I literally got a blanket and wrapped it around the annoying light source. That sort of minimized the glare and made our scans a lot cleaner. The actual sort of pipeline that we used here is take photos at different locations. And then once you find a location around the sort of object at hand, you take increments, angle increments, photos with the laser shining on the actual object. The laser line would then project itself and have different locations on the photo that you just took based on the distance away from your scanning unit, your scanning module. Now, that would give us sort of depth, a sense of depth in terms of the object. And given enough scans with enough angles, one can recreate sort of the collection of points to make partial map of the object. Basically scan a side of it and have a rough estimate of how basically tell your computer roughly how it looks like. The way to do that is to try and tackle the issue of taking photos and trying to extract very, very specific information from the photo. We used an HSV mask, and that was then layered on top to try and draw purely the red. Now, you face more noise issues, one of which you can see on the screen right now, which was the very old ladder that we used and a very nice person allowed me to borrow. That was also confused for the light, which caused its own noise. Now, let's say you go out and scan, you do all that. The next step is you do not have one unified scan. You have multiple face scan. As we can see on the video at the very bottom right, there are multiple faces at hand, and each face has its own orientation. Sometimes they're sized differently because, again, it depends on how far you are from the object. And all of those faces have to be sort of meshed together and cleaned up. There's a lot of noise. There's a lot of fluttering points here and there. So for a lot of it, sort of the attitude I had to take was, I'm going to scrub this thing clean. Between quotations, of course. I take away points here and there, and once it's all cleaned up, join them all together with a lot of moving points in 3D space, and we got this mesh over here. Now, a point cloud is only as good as what you can achieve with it. The next step to create a 3D model is to mesh it, which basically triangulates or creates polygons between those points in your point cloud and makes a solid body that the computer can now understand as a surface, as opposed to a collection of random points in 3D space. On the left, we can see our first attempt, which is nothing like the object, and it doesn't know where it is. The right side, if we redo this again, showed us a much cleaner one, and we achieved it by basically taking random samples from the point cloud and basically rendering it down, which allowed our density, which wasn't very uniform. It was very dense, but not very uniform, to sort of drop in the noise and the slight differences in point dimensions. We basically tried to minimize the noise achieved by it, and we managed to get a much cleaner mesh. The last and final step, and arguably the most proud step of all, is to take that mesh, clean it up, fix all the holes, make it watertight, as many programs like to dub it, and we get our very own STL file. And once you get an STL file, you can then upload it to any sort of slicer of your kind, whatever kind you use, and actually make a 3D model of said object. One that I'm very, very excited to give to Dr. Mitchell, and hopefully can give me more advice towards it. But this was a very, very exciting project, a very important teaching moment, and I feel like a more capable engineer having done so. Thank you for listening, and thank you, Professor Mitchell.